will be recorded in WebEx and then YouTube. And because YouTube needed some time to require some time to editing, so maybe this class will be uploaded by tomorrow, I think. Okay. So today's class is about the Prolog computer algorithms. So last class I have talked about. Oh, let me see. That's this slide. I'm sorry. This guy, not this one. How about this one? Oh, not this. How about this one? Okay, yes, I think I used this. Okay, so last class I talked about what is algorithm. Algorithm is kind of step-by-step description to solve a problem. So you want to solve a problem, then you have to you may need some logic to solve it, and the logic can be described within some formal way, like a step-by-step, the 1, 2, 3, 4, 5 step-by-step way, or logic can be written in some kind of a mathematical notation, or you can tell the logic by yourself, by your own language, natural language, or you can draw some picture to describe step-by-step logic. Okay, so likewise, algorithm can be written with several methods like mathematical notation, or maybe you can using some your own natural language. Natural language is kind of a thing, just your natural speaking thing, right? And then sometimes you may need to do something to describe your own logic. So algorithms can be written like this way. You can draw something, or you can say something, or you can make some mathematical equation, and then you show such equation to the your other people, other colleague or other engineers. Also, algorithm is usually the most main focus of algorithm is about programming things, software engineering, coding. So algorithm can be programming source code can be itself be can programming source code can be algorithm itself. So you can write down algorithm with programming source code, or you can write down algorithm using some kind of, let me see. Okay, okay. You can use algorithm with some kind of, I mean the, I'm sorry, some kind of, yeah, yeah, a mathematical notation, or yeah. Anyway, so maybe if you have an idea to solve a problem, then maybe idea is idea. Before you write down or publish your idea to others, then nobody knows your idea. Or even you don't have any intention to publish it or talk to others about your idea, sometimes you have to write down, you have to summarize your own idea to verify. If you have your idea inside of your brain, then maybe you can think twice or third time, 3 times, 4 times to think about your idea is correct or not. But it's better you write down your idea by hand in the note, and then by watching your note, that will give more better. They will be better for verifying your ideas correctness. So algorithm is kind of thing about what to do to solve a problem, and we can say this kind of logic. And if you want to say your algorithm, or if you want to keep your idea in your brain, but it's better to write down in some place, and then that will give more that will be better for checking, verifying your idea is correct or not. So there's many methods to write down algorithm. One is mathematical notation. So sometimes you can summarize your own idea with some kind of mathematical notation. Not for all the problems. Some problem, especially some mathematical problem, or in computer-wise communication, signal processing, or some area. One line of equation is much better than several line of word. Okay, so you can use mathematical notation, and you can use natural language. Natural language is kind of a speaking word you are using. Just you can tell something to your, likewise you say something to your friend or your teacher. Natural language works like that. Okay, and graphics is just a kind of drawing. So there is pros and cons about each method. So based on your intention, or based on usage of your algorithm, you can choose one of them. That's the most you can choose the most useful one by yourself, and then yeah, that's it. There is so programming source code. Let me see. In programming source code here, yeah, there is programming source code. It is source code. So once you build a source code, then you don't need to programming work anymore. That means it is already source code, right? So just you're using source code, and you already have a source code, right? Based on your logic, then just you can learn it. You don't need much work. Just you compile it and learn it and watch the result. That will be fine. So it's good, but there is downside. It's upside. It's a downside. Okay, it's upside. Upside, downside, hard to read and hard to verify. Yes, it's source code, right? The thing is, source code usually have source code usually have many things like variable management, pointer, as well as algorithm logics. So inside of source code, there's many things. Just what you want to is just want to see the logic of your some software system, but inside of software system, inside source code, there is many other things inside together in the source packed into together into source code. So it's hard to read, hard to verify. So and the mathematical notation is better to in this case. Upside for expertise, good for understand, for clear understanding. There's no mismatch. There's each mathematical equation. So there's in some case, many people may misunderstand the meaning of the notation. But if you're using mathematical notation, then it's very clear. There's not much misunderstanding for some kind of algorithm. Also, the other one is it is easy to verify correctness and performance. So that is but downside But downside, for newbie, hard to use this and how to use it. That means need training to write and to use it. So and need more work to code because mathematical equation is just an equation. So if you try to this kind of mathematical equation into your programming source code, then you have to you need several steps like decomposing equation and assigning value, blah blah blah. Because, for example, you are using you want to create some summation, or some summation operational function. If you want to create some function into C language, then in mathematical notation is very simple, just a summation with some symbol, that's enough. But if you want to try to if you try to code those kind of equation, then you have to assign, you learn some loop, and you have to have some return value, you have to see intermediate values. So more work is needed to code from the mathematical notation. And pseudocode is not code, but code like sentences. So it is not code, but anything that looks like a source code, but actually this is not applied. So maybe it is simpler than to coding thing. Code like sentences. So not I'm sorry. Okay, code like sentences. So that is pseudocode. Maybe it is simpler than pseudocode. So it looks like a source code, but this is not this does not work like a source code. This pseudocode cannot be compiled. If you try to compile this pseudocode, then if you try to build the pseudocode using your own some programming tool, then there would be a bunch of lots of error message comes out. So pseudocode is not code, but it's something that is not code, but it's code like shaped and shaped sentences, and then it's simpler than source code. So not include anything but programming logic. Include okay. So pseudocode is kind of so maybe I will give the example. I will show the example later in natural language. Let me explain natural language. Here is natural language, and this is upside. Simple to say or create. Downside. Ambiguous. So misunderstanding could happen. So that is, and then in graphics, upside will be easy to understand. in graphics means you are building some kind of graphics here. Let me see. Graphic here, building something, and then there is some arrow here, and then some other arrow here, and do something here, right? If there is some loop, then maybe you add some go back loop here. So within the rectangle, you write down some description or some steps. So this graphics graphics algorithm written with graphics is easy to understand, but the downside will be takes time to draw. Yeah, that is downside. So let me see here. So like this. So there is pros and cons. So when in case if someone asks you to describe your own algorithm, but you don't have much time or you have to answer immediately, then it's better to using natural language. Or someone may ask you about the algorithm, but he or she doesn't require formal format. Just she or she wants to hear your idea. Then natural language is better, much better solution. Just saying something, maybe he or she may question if there's some misunderstanding or there is some unclear thing. Then you can answer, you can explain your own idea in more clear way. So natural language is very good way in such case. But if you write down research paper, then mathematical notation will be much better because it's very clear and it's for the expertise, not newbie or new one. And mathematical notation is if your research work you want to show your research work works better or correct, then with the mathematical notation you can show your solution is correct or your solution works better by proving some mathematical things. So if you are usually in research work, research work means you have to build something new, something better. So in mathematical notation, the algorithm written in mathematical notation is useful for showing your original approach, your own work is correct, or showing your work works better. Okay, so but in programming, source code is kind of pseudocode is like thing like that. In some case, it's very hard to explain, or maybe your explanation can make some confusion. But in some case, your solution is not about mathematical thing. So your solution is nothing more than not it does not relate. Your solution is not related to a mathematical thing. Then, but you need to explain your own algorithm. Then pseudocode is good way. Just writing down something, some code-like structure, but inside of code, rather than including your source code, because source code is very long and source code includes very unnecessary information. So remove everything unnecessary thing that you just showing your own logic itself with pseudocode format. So in most research papers using this guy or this guy or this guy, and graphical notation is for the presentation, or sometimes you have to make some record of your own logic, and there would be some chances for educating your new guys. So yeah, graphic solution is good for presentation or good for record. Record means you make some your own algorithm, and then if you build graphical way, then maybe later you can show your algorithm to others, or you can show your algorithm to your friend. So this is better for presentation because this approach is easy to understand. Okay. Let me see. Yes. And then here is one example of an algorithm in Fibonacci sequence. Fibonacci sequence is actually I know you already know all of you already know what the Fibonacci sequence is. The Fibonacci sequence is the definition is each number in a sequence is the sum of its two immediately predecessor. So here is Fibonacci sequence. So first element is 0, second one is 1. 1 means first 2 is 2 immediate predecessor, 0 and 1. So using two numbers, third element will be 1 because using this sum. And then fourth element is using second and third element. By adding together, you can set up fourth element. So 1 plus 1 equals 2. So this is a Fibonacci sequence like this. So it's a kind of definition here. So it is like this one is this one is written with natural okay. So here this is about natural language the explanation. So you can see here each number in a sequence is the sum of its two immediate predecessors. So it looks like clear, but maybe some of you may not understand what is it. Maybe it will be need some time to understand the definition of a Fibonacci sequence. So here, so this is the example. So like this, so look at this. For this example, the first equal 0, the second 1, third will be 0 plus 1 plus fourth 1 plus 2 or 1 plus 1, so second plus and fifth 1 plus 2 plus and so on here. So this is Fibonacci sequence. Actually, this is not new one. I know in high school, in textbook include Fibonacci sequence. I know that, so I think all of you already know what the Fibonacci sequence is. So here is definition, but it is sometimes unclear. So here is another definition. Here it is a mathematical notation definition, right? Mathematical. So here is the one. Fn equal Fn minus 1 plus Fn minus 2. You can see here each number in a sequence is the sum of its two immediate predecessor. Each two immediate predecessor, look at this value. So this guy is about this guy, immediate predecessor. It's Fn. Each immediate predecessor will be, so this guy is this guy nth number, and two immediate predecessors. So this is about n minus 1th number and n minus 2 number here. So this definition, this is natural language, written like with natural language. This is written with mathematical notation, and maybe I don't know, because Fibonacci sequence is familiar. I think you're familiar. All of you are familiar with the Fibonacci sequence, so maybe I believe most of you prefer this kind of definition rather than this kind of definition. So that's why in some research paper is using this kind of mathematical notation, even though this mathematical using understanding mathematical equation is hard, but by some training, then you will find out, okay, using mathematical notation is much better in describing your own logic in some cases. Fibonacci sequence. So maybe if you can, if you're teaching someone, then you can say something like this way. But if you write down or writing down some report, then you may prefer this format because you know this is a more clear way. And then one more thing, if you write down this way, then you will find out some missing point, two missing points. One is this guy is using two immediate predecessors. So that means the second one and fourth one, first element and second element should be defined with this format, because for the first element there's no predecessor and second element has only one predecessor, so you cannot use this way. So, but maybe this definition looks okay, but by writing down mathematical notation, maybe you find out some missing point, because using this equation, this is n and 1 minus 1 and minus 2, but first element and second element cannot be applied, to the this equation cannot be applied to first and second logic, okay, and second element of Fibonacci sequence. So you need to add more definition like this way. So if n equals 0, that means it's the first element, and here the second element, okay. So you have to define another number like this. So anyway, using this kind of Fibonacci number itself grows exponentially as fast as the power of 2. So question of computational problem try to solve using Fibonacci sequence is this defined like this. What is nth Fibonacci number? Okay, so now you have a goal to solve. You have a goal to make a program, right? So so here is code like this. You have definition like here and definition like this. So using this the thing you only know is definition itself. So here is 1 and 2 definition like here, and this is the nth number. So nth number, n minus 1's number, n minus 2's number. So as you can see, this f. So by using this property, you can define the Fibonacci number logic like this way using recursion. Okay, recursion is kind of, you can say JAGI. JAGI is a little bit complex thing, but recursion. Okay, so this is recursion. So you look at this way. Look at this equation. It's f1 equal, I'm sorry, fn equal fn minus 1 plus n minus 2. So p of n is written p of n minus 1 plus n minus 2. You can see here. And then if n equal 1, then number will be 1. If n equal 1, then number will be 1. If n equal 0, number will be 0. 0. So same, right? So here is the format of pseudocode. So look at this. Here is natural language description. Here is mathematical notation. Here is pseudocode. Why this is pseudocode? Because this is not written in C language or Java language or Python. So if you try to copy and paste to your programming tool, then programming tool will show bunch of error, lots of error in your screen. So this is not working for actual programming, but the shape is very similar to programming source code logic. So that is, we call that the shape is looks like code but not working to compiling. Okay, so this is pseudocode. So you can see n equals 0. So then why we use pseudocode? It's simple. In this case, you don't need to define no need to in pseudocode no need to define variable or return type or variable. So in define and variable and no need to consider return type. So just a simple, you in the pseudocode, you only write down your own logic. Okay, so that's why people prefer using the pseudocode when people need to explain or describe their own logic. Okay, so in source code itself, you have to define something like int n and maybe int p or something, but not the length will be not much different because it's very simple code. But if you are using you are building some more complex source code, then 100 line, 200 line will be common thing to for each 100 line of source code, 200 line of source code is very common for because in the source code you have to define something, and sometimes you need to some kind of intermediate variables. So here is the one, right? So yeah, but if you're using source code, pseudocode, then total length will not be like that big size, like 100 or 200 size. Just 10 lines of code. Sometimes 10 lines of code will be enough, right? Because you don't have to care about variable creation, variable management, or loop assignment, or some more pointer assignment, or some error condition management. Just you only need to describe the logic itself. So pseudocode is a code-shaped thing. So that means you can understand easily when you are familiar with the source code. Then also that is short, much shorter than source code. So that is kind of advantage over the actual using programming source code. And then once you have it, then next step is checking correctness and checking efficiency. Here, so is it correct? Yeah, correct. Since we use mathematical definition directly, this algorithm will be definitely correct, because that is definition of mathematical notation, and we are using this notation directly to the building pseudocode. Look at this fn minus 1 plus n minus 2, and look at this p n minus 1 plus p n minus 2, and 1 0 1 0 like here. So it's correct, it should be correct. Just we translate, not translate, just copying something. We use mathematical definition directly, and then next step is, once you verify your algorithm is correct, then next step is you have to analyze efficiency. Then because this is algorithm, so since we are on the algorithm design stage, we don't have source code or execution files, so we need another method to measure so how to do that? Just calculate the number of execution steps by watching pseudocode or source code and count them one by one. So if there's many count, then that means the algorithm require more steps. That means the algorithm will be slow. And if the algorithm doesn't require much step, and then algorithm, we can say the algorithm finish it faster. So we need to calculate the number of execution steps. But before we calculate the execution step, we need to make some basic assumption. The assumption means every operation only takes one step. Actually, actual programming language like C or assembler language, addition and deletion takes shorter time, but branching takes longer time, because branching means that there's some movement here of control point in the source code, and loading data takes much longer time, because it sometimes you need to access memory or access the hard drive or SSD. So every operation does not take equal time. Just some operation require very longer step, and some operation require shorter step. But we cannot consider this kind of thing, because each based on machine by machine. So in some machines, some CPU take each CPU by CPU, every step will be different. Some machine storing, loading take a shorter time, and some machine addition, multiplication runs shorter than other machines. So it's too many variables, too many things we have to consider. So what we want to is calculate an algorithm execution steps. So we assume that we need to simplify computing step. So we assume that first we have to assume that every operation takes only one step, not many. Even though in reality, addition, deletion take a shorter step, and loading, storing data takes a longer step. So like this way. So here is the example. There is some command line. There's 1, 2, 3, 4, 5 return. So and there is some kind of this. There is option. If else, there is option thing. So we can say that the total number of steps will be 5, because 1, 2, 3, 4. and return 5. So we can say, okay, this guy takes 5 steps, but actually it's based on machine by machine. This is assignment. Assignment in some machine takes 3 steps, some machine takes 5 steps, depends on CPU. And multiplication, some machine take 15, some machine takes 30. It's based on machine by machine. So you cannot say clearly this take what kind, this take 3, this take 5, this take 15. You cannot say the way, because every machine has their own logic in mechanical design. So adding, multiplication, deletion takes that kind of characteristics of CPUs. So roughly we can say, okay, this guy is a 55 step, but sometimes it is very complex to calculate the actual step like this way. Why? Here is an example. There's a one loop here. Then in this case, let me see. Yes, in this case, each for loop, there is assignment I equal 1, and then there's a loop increase I from 1 to 2n, and inner loop, inside the loop, run x equal, run the statement x equal x plus 1. So total execution will be I'm sorry, let me see. Okay, I'm trying to recording this thing, but recording will be automatically stopped. So let me see why. I don't know. No, it's okay. It's okay. Maybe that is the kind of automatic stuff. So anyway, so look at this. So inside of loop, so like run the statement x equal x plus 1 here. Let me see that. X equal. Okay. So then total execution time will be there is loop 2n loop here, 2n times, and increasing I 1 plus 1 here. So the step will be because this guy is assignment, and this guy will be number of loop runs, and this guy is increase I, and this guy is run x equal x plus 1 statement. Okay, so total time will be calculated like this way. So yeah, this guy, so total step will be 1 plus 4n. So okay, so I'm sorry, I have to take a 5-minute break. Okay, after then I will continue my class. 5-minute breaks. Okay, I will have 5-minute breaks here. So Okay. 네, 수업을 계속 진행을 하겠습니다. 네, 좀 이렇게 보니까 좀 어둡네요. 사무실이 잠시 좀 어두워서 네, 수업을 진행할게요. Next example will be is second example is a double loop. There's two loop. This is outer loop and inner loop here. Outer loop is runs to n time, and inner loop runs n time here. So so there is assignment I equal 1, and there's a loop increase I from 1 to n, and there is a inside loop, another loop here, and inside the loop another loop, j what's wrong, j assignment j equal 1, and loop increase j from 1 to n, and inside loop run x equal x plus 1. So here is the number of execution. So using this property, we can calculate total execution time equal 1 plus 1 is assignment, first assignment, so 1 equal I equal 1, so plus there is loop 2n loop, and inside loop is 1, so number of loop 1, it is increase I plus here is another loop, so another loop equal 1 plus n times 2, right? And it is j equal 1 plus n 2, n times 2, that means increase j plus run x equal x plus 1. So there is this guy total step is another step equal 1 plus 2 n times 2, right? So total step equal 1 plus 2n, 1 plus 2n, so equal 1 plus 2n plus 4n square. So that is total step. Okay, so this is for this double loop. Total execution time will be calculated like this way. So sometimes it is very complex to calculate execution steps. So like this kind of shape, you can see this equation, and then use for the double loop of single loop, the total execution time, total step will be 1 plus 4n, 1 plus 2n plus 4 times n square. That is the total execution time. So calculating this kind of thing will be complex, as you can see here, will be very complex. And look at, let's see another final example number 3. Oops. Yes, oops. I don't know. Okay, let's forget this thing. Why this guy is not moving? I don't understand it. Okay. Oops. Okay, now, okay, that's fine. So let's see, maybe this color here. So there's triple loop. So assignment in third position, I equal 1, but loop increase I from 1 to n. But there is another loop inside the loop. Maybe also there is inside the loop. It's more complex because there's triple loop, and also the ending point is I, not n. I is depend on this guy, so it's more complex. So this is the example. This is a very short example, but when you try to decide the action step from your own idea or your own source code, definitely it will be very much more complex. So for this reason, this is, even though calculating the execution step is only way to measure the efficiency of your own algorithm, but it's not that good thing to verify the execution time. So rather than we focus on source code itself, maybe we can think about the basic context of this system. So this loop here, the goal of this loop is run this statement several times. How many times? 2n, right? For this goal of this kind of thing is the running this guy in double loop. So how many times this guy runs? This is 2n square, right? This statement, the goal of loop is run this statement repeatedly, the goal of the learning loop is repeatedly learning some statements. So maybe if we, because we already using some basic assumption, every action, every statement runs the same time, one step. So since we have already used some kind of basic assumptions, so maybe it is not usual thing to add another assumption to simplify something. So in this case, rather than we so cause source code complex calculating execution steps will be complex. So we need but note our measure efficiency of algorithm logic, not to calculate exact steps. So we need more simple way to describe the measurement of algorithm. Okay, so just so how to do that? Just focus on the core. Focus on the number of execution of core statement. Here, x equal x plus 1 will be core statement. The reason to using loop is just learning this statement several times, right? Just the reason to using this kind of loop is just learning this statement several times, not once. So just what we need to do is just measuring how many times. So measure many times x equal x plus 1 is executed. Okay, so we need to simplify this kind of thing. How many times this guy is running? Okay, not the actual actual execution like I equals and 1, and then I increase once by one, and then during that time x equals x plus 1 is once. Rather than calculating all the steps, just focus because this is too complex and this is a kind of thing over our interest so we only need to focus on the how many times this state runs. That we just by um, uh, focusing on this statement does not make any different result, because what we are interested in is just is it runs for long time or short time. That is our interest, right? Not the actual steps. So just measuring how many times this statement is executed will be enough for our focus, right? So usually, so now just to forget about this. This is basic mechanism. So just focusing on the core state, how many times that this kind of core state was executed. Okay, so and also when we are trying to using this kind of equation. that's calculating. Let's go back to this example, and then we are going to try to figure out how many times this kind of module runs. And look at this, there is some kind of if-else statement, and then there is some function call, but it is a recursive function call. So we can measure total execution step one by one for this kind of statement, but for this statement we cannot measure by counting, because inside of this function there is another operation will be needed. Also inside this function there would be another operation. So in this case we need some kind of thing like this way. So Tn is, here is Tn. Tn and is the number of execution of pip n, okay, and then Tn minus 1 is n minus 1, okay. So we can solve this kind of thing using recurrence relation, and I think some of you already learned it. I think some of you already learned it from the course discrete mathematics. Okay, so but you don't have to worry about that. Maybe many students, I think, some students already have not taken any class about the discrete mathematics course, but maybe in next class I will show the some basic notation about this discrete mathematics, and then I will show how to calculate with this kind of situation. Okay. So anyway, during this calculation, we have to identify result will be like this, very slow. So this is slow. So even though the algorithm is correct, but with this kind of speed, maybe we may have to improve the execution time for the code. So maybe the idea is store some value to avoid some same computation. By avoiding same computation, maybe we can say that we can improve execution time. Here is the example here, Fibonacci number, and to calculate the Fibonacci n, and Fibonacci n minus 1 and n minus 2 is calculated. Okay. Also, to calculate the pivot n minus 1, we need to calculate the pivot n minus 2 and n minus 3. But as you can see here, pivot n minus 2, n minus 2 is same. So you see pivot n minus 2 is computed twice. But pivot n minus 2 n minus 2 is unnecessary if you store result of pivot n minus 2 when you need to compute pivot n-2, use the stored value for pivot n-2. So the original solution here, original algorithm here, when you need to pivot n-1, then maybe you have to call recursive function again to calculate the pivot n-1. So again. But in this case, as you can see, n-2, in this case, there's some duplication. So the original solution, even though you calculate this kind of pivot n-2 by some recursive operation, but you have to do that again for this situation because this function is called again. So there's no way to calculate but calculating same thing again over and over. But if you store this value in some place, the result of this value in some place, then when you face this kind of thing, you don't have to compute again. Just you ignore them and just using the result of that value for this operation. So you can avoid the same computation. So by avoiding same computation, you can improve total execution time. Okay, so here is improved version of Fibonacci number logic here. So there is some number here, pivot beta. There is a function called recursive function called here, but rather than returning these values, okay, I'm sorry, this is not equal, this is plus value. So rather than returning directly, store the value inside some array here and then returning array value here. But if the array is not available, that is array is initialized as a -1. So if this array is not available, then compute Fibonacci number by recursion. But if you already have the number, then you don't have to compute it, just return FM value. That will be, yeah, that is, you don't have to do that. So you finally finish the value here. So yes, so you can avoid total execution steps. So definitely final result will be total execution time of improved version will show much better performance. Okay, so that is basic thing. So okay, so today's class ended so far, and I'm sorry. Again, I have to say sorry about some lateness of today's class. So because I have internet problem, so maybe I hope there will be no problem before my class. So you can come to my class on time and you can listen my lecture on time. I hope so that. And actually, I never have, because with the Corona season, this is third semester. I'm teaching you online with the WebEx, but I never been. I have never been late so far. It's first time, so I'm sorry again. So anyway, thank you for listening. For maybe this class will be uploaded in WebEx and YouTube together. So anyway, thank you for listening to any YouTube or WebEx. But anyway, see you next class on Monday. And in Monday class, there's actually Monday class you have to do some programming practice. But in next Monday we will have a written practice about this kind of thing today's class. So you don't have to prepare for programming tool for next Monday. But yes, okay. Thank you so much. Good night.